Hello everyone. Welcome to the third lecture of this second module where we are discussing the characteristic of sensors. In the previous class, we have discussed some of the static characteristics that include stability, nonlinearity, hysteresis, repeatability, reproducibility. With this, we have also discussed some error like repeatability error. Okay. I hope that those concepts are clear to you. Let us discuss some of the more characteristics that are very relevant to the practical sensors. Okay, one of such characteristic is a deadband. Okay, deadband is the insensitivity of a sensor in a specific range of the input signal. Okay, in that range, the output may remain near to certain value. Mostly this values is 0 over an entire deadband zone. Let us understand this with the data. Okay, this is a transfer function of a sensor. Okay, if you see in this range, the output is not changing. It is remaining 0. Okay, even if you increase the input. Okay, this zone is known as deadband. Okay, you should always avoid operation of your sensor in deadband or dead zone. Okay, next concept is resolution. This is the smallest increment of the stimulus that can be sensed. Okay, this resolution is the smallest distinguishable change the sensor can detect and display. The higher the resolution, the more specific are the values. Please do not get confused between resolution and accuracy. Accuracy is the sensor's degree of veracity. It means that it is the degree with which how close a measurement gets to the actual or the known values. Okay, it has nothing to do with resolution. Okay, let us understand this with one example of again with a gas sensor. Okay, I have two sensor X and sensor Y. Okay, this is the dynamic curve of this sensor. This is for particular gas. Let us take a gas A, and for the same gas, if I see the response, okay, this is the response for these two sensors X and Y. This is for concentration, say C1, C2 and C3. This is for C1, C2 and C3. Okay, this is the response of this sensor for particular gas A. This is the response for two different sensors X and Y. Okay, now say this sensor X can measure concentration till C100. Okay, so this response continues and I have a value for C100. Okay, however, this sensor, this Y, cannot go to C100 and it can only measure say till C5. So I have C4 and C5. Okay, this is for concentration C4 and this is for C5. All right, say a person need to measure some concentration which that concentration lies between C2 and C3. Okay, now even this sensor X has very large dynamic range. It can measure from C1 to C100. However, Y can only measure between C1 to C5, but the person's need or person's requirement is to measure some concentration between C2 and C3. Okay, so while choosing, he will not see the dynamic range. He has to see the resolution of the sensor. If resolution of sensor Y is better, okay, even its dynamic range is poorer than sensor X, he has to choose sensor Y. Okay, I hope the concept of resolution is clear to you. Okay, let's move to another characteristic which is output impedance. Okay, output impedance is very crucial for a sensor, particularly if you see from interface circuit design point of view. Okay, output impedance, mostly denoted by Z out, is important to know for better interfacing of a sensor with the electronic circuit. Okay, output impedance is connected to the input impedance of a circuit either as a voltage connection or as a current connection. You can see a sensor has a voltage output. In case B, sensor has a current output, and it is connected to the interface circuit, which is this right hand side portion of this figure shows the interface circuit. Okay. Output and input impedance generally should be represented in a complex form, as they may include active and reactive components. Okay. To minimize the output signal distortion, a current generating sensor, this figure B was a sensor where current is there as an output. Okay. So for this condition, the condition B, a current generating sensor should have an output impedance as high as possible, while the circuit's input impedance should be low. Okay. However, for this condition A, for this condition, okay, a sensor is preferable with lower Z out, while the circuit should have Z in as very high. Okay. Practically, the input impedance of this interface circuit is very high if the sensor is a voltage generating device. Okay. This is a thumb rule you should always remember while designing a interface circuit for a sensor. Okay. Another important characteristic is excitation. Particularly, it becomes very crucial for designing active sensors. Okay. So it is the electrical signal which is needed for the operation of an active sensor. It is specified as a range of voltage and current. So sometime you may have to design excitation circuit for an active sensor to perform. Spurious variation in the excitation may alter the sensor's transfer function, and it may cause the error in the output. An example of excitation signal is, say for example, is given here. You have a maximum current through a thermistor in air as 50 microamp, in water you have 1 milliamp. Okay. So you have to design the excitation circuit in such a way that it fulfills both the condition. Okay. Similarly, your sensor may have different requirement. Okay. Let's move towards another characteristic, which is response and recovery time. We'll take the same example of repeatability. Okay. This was the repeatability curve that we have studied. Okay. I have a current versus time curve for the device, for a microsensor. Okay. Now, let us see what is response time and recovery time of my sensor. Okay. At this particular position, I have applied the analyte. Okay. Or at this particular point, my sensor is exposed to some analyte. Okay. Now, it has reached to, say, this is the maximum value. Okay. Response time is defined as 10% of this value, or the time it takes to rise from this particular value, say this is 10% of this value, to 90% of the maximum value. Okay. This time frame is known as response time. Similarly, same concept is applied for recovery time. So time taken from 90% of the maximum value to 10% of the baseline value. Okay. This definition has been under debate. Okay. However, till now we are using this definition. Okay. This is very crucial, particularly for sensor which doesn't saturate. Okay. Say if I have a response, okay, consider that I have a sensor where this is, say, baseline, and I have introduced some analyte X at this particular time. So this is time versus, say, resistance. Okay. Now I have switched the X off at this particular time. Okay. Now ideally it should come to this position, but it is not coming. Okay. It keep on increasing, and then it start decreasing. If you see, you do not have any saturation value. Okay. For these cases, it is better to define as 90% of the maximum value rather than getting confused. Okay. So this is how a response time and recovery time of a sensor is defined. Okay. Let us see some of the environment factors which hampers the sensor's performance. Okay, consider the storage condition of a sensor. Okay, usually storage condition includes the highest and lowest storage temperature and maximum relative humidity at this particular temperature, and together they are known as humidex. Okay, depending on the sensor's nature, some specific limitation for the storage may need to be considered. For instance, maximum pressure, presence of some liquid, gases, or some of the contaminating fumes which may hamper the sensor's performance. Okay, these environment factors or the storage conditions may affect the short-term and long-term stability of the device. Okay, what is short-term stability? This is manifested as change in the sensor's performance within some minutes to some hours or some days. Okay, eventually it is another way to express repeatability, as drift may be bidirectional. Okay, sometime you never know that, say in the daytime temperature is say 40, it is reaching to say 40 degrees Celsius, while in night it is reaching to 23 degrees Celsius or say 21 degrees Celsius. So if I have this as a baseline, in the daytime I may have an increase because of say thermal agitation in the sensor's receptor. Okay, and it may go down to this particular point. Okay, so if you see, this was my original baseline. It is drifting to some higher values in daytime, and in nighttime it is decreasing. Okay, so because of this ambient factors, okay, the drift can be bidirectional as well. Okay, so short-term stability is very crucial to be defined. Okay, the sensor's output signal may increase or decrease, which is then in terms may be described as ultra low frequency noises. Okay, so this increase and decrease, in the baseline can also be manifested in the sensor's response. Okay, so if you are measuring some value at this particular point, okay, you have to compare. Say I have this is as baseline. If I do measurement here, I may have response over here. Okay, say if baseline has gone here, if I'm measuring, okay, same concentration, okay, this may be our response. Okay, and say this baseline has decreased due to the ambient condition in night. Okay, the response will be this. True. Then there is long-term stability. This is related to aging of the sensing, particularly the sensor material, okay, which is an irreversible change in the material's electrical, mechanical, chemical or thermal properties, and this is unidirectional. Okay, so once this aging thing has happened, okay, you cannot bring back its properties. Okay, so mostly this long-term stability has to do with the shelf life of the device also. Okay, now let us discuss one important concept, which is the concept of noise. Okay, noise is very crucial for the operation of a microsensor and a nanosensor. Okay, noise is the spurious current or voltage which is irrelevant to the signal current or voltage that you are measuring. Okay, the signal can be generated through the microsensor. Okay, and usually there is one term which is known as signal to noise ratio, is very important to be understood for better operation of the device of the sensor. Okay, so signal to noise ratio is basically the ratio of signal power to noise power. Usually your power is directly proportional to voltage square. So signal to noise ratio can also be written as the signal of interest in terms of voltage square divided by unwanted noise voltage square. Okay, so if the unwanted signal is lesser in magnitude, means your signal is dominating, then signal to noise ratio is very high. Okay, and in those conditions I can say that noise is say negligible. However, in most of the cases this is not the condition, particularly while you deal with microsensors and nanosensor, where the signal itself is in some nanoamp or sometime it goes in picoamp also. Mostly the noises are dominating in that particular range. Okay, you can also define signal to noise ratio as the ratio between mean value of the signal by standard deviation of the noise. Okay, sources of the noise is very crucial to be known for the better operation of these devices. Okay, noise can be caused by both from the external ambient or from internally generated sources. Okay, external sources of the noise can be some electromagnetic signals produced by some other, say, big instrument kept in the lab next to my sensing measurement setup. Okay, it can be produced by some transmission, say, reception circuits. Some power supplies can also produce it. Some mechanical vibration that is coming from some heavy instrument or some heavy motor which is running nearby to the sensor's measurement setup. Okay, and biggest source is the ambient temperature itself. Okay, these external sources can produce some systematic error in the device. Then I can have some internally generated noise. Okay, I call it say internal sources of noise. Okay, its nature is totally different than external source noise. Okay, mostly this internal generated noise or internal source of noise is of three types. One is generated noise, second is conducted noise, and third is radiated noise. Okay, let us see them one by one. Okay, let us understand the generated noise first. Okay, consider that I have an amplifier. Okay, I am providing it one input signal which is not having any noise. Okay, however, at the output I am expecting that this amplifier will amplify the input signal. However, at the output what I am getting is I am getting a amplified signal but with some noise. Okay, here I have not used anything. I have only used a power supply or a DC biasing for this amplifier for its operation. Okay, then also at the output I am getting a noise. Okay, so from where this noise is coming? Okay, I am not using any other external ambient and this setup is completely enclosed. Then also I am getting some noise. Okay, this noise is actually getting generated inside the amplifier only. Okay, so this can be a possible source that the internal components of the amplifier, like it is built up of some active element and some passive element like some resistor, capacitor, inductor, say some transistor, diode. Okay, so the noise is getting produced in those active and passive components. Okay, so let us understand this generated noise by some more relevant noise to this resistors and transistors, which is Johnson noise. Sometimes it is also known as Johnson-Nyquist noise. It is also known as Nyquist noise, and sometimes we call it thermal noise. Okay, conductive portion of a resistor consists of a regularly arranged group of atoms. Due to temperature and thermal effect, they are in a state of rapid vibratory motion. Okay, this vibratory motion of atom is transferred to the conduction electron, which produces noise component of current. Okay, this noise increases with internal heating, or this noise is temperature dependent, and this noise is called Johnson noise. Okay, I have mentioned that due to temperature and thermal effect, the atoms of the resistor are getting disturbed or is having some vibratory motion. Okay, so this motion, the kinetic energy of this motion is say half mv square, where m is say mass of the electron and v is the velocity of the electron. Okay, this energy is transferred to the thermal energy. Okay, say if I am talking about a T at room temperature, so I am talking at typically at 300 Kelvin. So this energy is converted to some say value of say kT, where K is my Boltzmann constant and T is the temperature. Okay, so if I have to find the value of this velocity, okay, I will have something like 2 kT divided by m under root. Okay, and this value is something say 10 power say 5 to 7, okay, depending on what temperature you are talking about. Okay, so this noise is basically a Johnson's noise. Okay, and it increases with internal heating. Okay, Johnson noise, as I have mentioned, is also known as Johnson-Nyquist noise or thermal noise because it was first measured at Bell Lab by John Johnson, and Harry Nyquist was able to explain the results to whom Johnson described in his finding. Okay, the amount of Johnson noise generated by an electronic resistor depend on its operational temperature and applied the range of frequencies. Okay, so Johnson noise can be given by a potential V as under root this KTRB, where this V is open circuit Johnson's voltage, K is the Boltzmann constant, T is the temperature, R is the resistance of resistor in which we are measuring this Johnson's noise, and B is the applied range of frequency, the bandwidth. All right, so this is 2 under root KTRB. All right. Let us see that if we can figure out some basic circuit for this noise generation. Okay, so noise power say Pn is generated as say Pn as Kt multiplied by its bandwidth. So where K is the Boltzmann constant and T is the absolute temperature of the resistor, and Kt multiplied by its bandwidth gives the noise power generated. Okay, the noise generation system can be represented by a voltage source of magnitude in series with equivalent resistance. Okay, so let us see equivalent circuit of a noise generation system. I can say something like this. Okay, if the noise generator is connected to an external load resistance, say RL, the noise energy will be transferred to the load. Okay, and under the condition of maximum power transfer, which suggests that this RL should be equal to this RN, the noise power is delivered to the load as something like this. Pn is equal to En square by 4Rn. This En square can be written as 4RPL or 4KT delta F, because PNL we have already seen that it is KT delta F. All right. Or I can simply write the value of this En as 2 under root KT delta F. Alright. So this is Johnson's noise. I hope it is clear to you. The vibrations produced by the thermal effect within a resistor cover a wide frequency range, and therefore the noise generated consists of a wide spectrum of frequencies. This wideband noise is sometimes also called white noise. Okay, the power spectrum density is defined as the noise power per unit of the frequency bandwidth, or Sn is defined as Pn by del F. Okay, or it is simply Kt, because I have seen that Pn is Kt del F. Okay, so thermal noise in an ideal resistor is approximately white in nature. Okay, it means that the power spectral density is nearly constant throughout the frequency spectrum, but it decays to zero when you go to very high frequency. Okay, when limited to a finite bandwidth, the thermal noise has a nearly Gaussian amplitude distribution. The conditions are very similar to the white signal. Okay, so with this, I hope that the concept of noise is clear to you. Okay, particularly the Johnson's noise. There are some other important noise in case of microsensors, because I am using semiconductor material as my channel or as a receptor. Therefore, knowing noises which is very relevant to the semiconductors, particularly the short noise, is very crucial. Okay, so in the next lecture we will discuss short noise along with some more noise signals. Thank you.